So, the solar system for strange things that we could attribute to impacts. So things that we look at, we see planets, and they're not quite right. There's something a bit odd about them. They're orbiting the wrong way. They seem to be upside down or on their side or something, which we think might be related to impacts in the past. You've already looked at some of the debris. You've looked at meteorite specimens. You've looked at bits of rock and metal, which are the fragments, the remains of these giant objects from space that we think smash into the Earth. I have a bottle of water here. You are roughly 50% water by mass, so if we dehydrated you just before the police dragged us away for sticking you in a microwave oven or whatever, if we took all the water out of your body, maybe half of that water has come from space. We're still not quite sure about the actual amount, but roughly half the water in your body, half the water that falls out of the sky, half the water that was in the fog that grounded me at Bristol Airport for 3 hours this morning, comes from space. The other half comes from volcanoes. We think it's the steam that comes out of volcanoes. So maybe half the water in this bottle isn't from this planet. It's from somewhere up there and has landed on the Earth in the past in the form of a comet, a giant glacier, basically, a huge lump of ice. And we'll finish off by looking at the extinction of the dinosaurs. So when we think about how solar systems form, how planetary systems form, the models that we had 20 years ago were based purely on our solar system. We only knew of one set of planets, and that was our, well, it was 9 when I was in school, now it's 8 planets that you'll be taught about if you're in school today. So we kicked Pluto out. Pluto was a planet, now it's a dwarf planet, but there's a campaign to have it reinstated, but that may or may not happen. But the model that we had, the computer models and the ideas that we had about how planets were born, recreated our solar system, with little rocky planets close in and big gas giants far out. And the problem is, since then we've discovered maybe 4,000 planets around other stars, definitely 2,000, none of the 2,000 that we suspect we know about, but we're not quite sure. And none of them are like ours. None of these solar systems match ours. Ours appears to be a bit of a freak, a bit of a unique example, which is interesting because maybe that's why we have life on our planet. Maybe we are a really odd, a really unusual form of planetary system around a star. Or maybe all planets are weird. Maybe we just don't understand how planets are born. But we have a real problem now in that the models that we produce, the computer simulations and the theories, are very good at explaining how our solar system was born, but not very good at explaining how the other 4,000 planets that we've now discovered were produced. So we're sort of, the theorists are all up in arms now because the observers keep finding things that don't match their theory. But the basic model that we have, and this kind of seems to work with subtle modifications, a huge cloud of gas and dust collapses. Gravity causes it to collapse. And the central region becomes very, very hot and very, very dense, and that becomes the star. And my research is involved, as Tim said, in stars and black holes and that kind of thing. But the other part of my interest is in what happens around the star, about the stuff that doesn't form the star, but forms this huge swirling disk. So the star is spinning, it's rotating, and the material around it smears out into a kind of a flat pancake shape, but a huge, very, very long pancake, stretches out for enormous distances. You've got to imagine the star at the centre is very, very hot. The sun's surface is at about 6,000 degrees Celsius. So there's a very hot object at the centre, so the material close in is warmed up by that hot star. And the further away from the star you get, the colder it gets. So the sort of material that we're dealing with close in, it's only going to be material that can survive high temperatures, so metals. A little bit further out, temperature drops to a few hundred degrees, it'll be metals and rocks. And then further out again, it'll also include ice and gas and smaller materials. So you have what we call a temperature gradient. Hot close in, cold far out. And that means you have different materials forming in different parts of the solar system early on. So that rocky and metallic material that you were holding in there, those meteorite specimens, they would form close in. They would form in the inner regions of that disk. And further out, you get the icy, gassy material. And that's basically how the planets form. Inside, in the inner region, you have lots of little bits and pieces of rock that stick together. So little dust particles form pebbles. The pebbles collide and form boulders. The boulders collide and form mountains. The mountains collide and form things the size of continents. Those collide and form planets. We call it a bottom-up model. You start with small things, you get bigger and bigger and bigger and bigger. And that's how you make rocky planets, and that's fine. The problem is, further out in this region, if that model was how we built Jupiter and Saturn and Uranus and Neptune probably wouldn't exist yet. It's such a slow process to build such big planets, they wouldn't be there. So for the outer region of the solar system, we have what we call a top-down model. Lots of gas collapses down to form one big planet very, very quickly. So oddly enough, we think the outer planets, Jupiter in particular, formed first. The bigger things were formed before the little things. But we kind of think in our heads little things are quick to form, right, because they're little. But the way you stick those dust grains together to make rocky planets is very slow. Further out, the huge clouds of dust and ice that are out here can collapse very quickly and make big planets very quickly. 1 million years, and quickly to an astronomer is, you know, if I tell my wife I'm cooking tea and I say it's going to be done quickly, she doesn't wait 1 million years, but it's probably not far off. So how we make planets is all about collisions. It's either gas colliding and collapsing, or in the case of forming something like the Earth, it's these rocks crashing in. So the early solar system is a very violent place. A lot of heat energy released, a lot of collisions, but that's how you get those rocks together. And because it's so hot, the metal sinks in towards the centre. You basically have a molten blob of rock and metal. And it separates, just like milk does. So the cream floats to the top and the milk sticks to the bottom. The metals, the dense material, sinks to the centre, and you get a rocky outer skin and an iron core at the centre of a planet. And then later on, those planetary objects can smash into each other. So it's all about collisions. It's kind of a gigantic, terrible game of pool or snooker or something, where these planets are whizzing around. Now, they're whizzing around under the laws of physics, so we can kind of understand what's going on. But every now and then, two of them will be at the same place at the same time, and you'll get a collision. These things will smash into each other. And some material will be blasted outwards and be lost into the solar system and may eventually be found as meteorites, little bits of rock flying around. But in the majority of what happens is those objects merge together, so you get a bigger planet. So this is another way of kind of making planets slowly get bigger and bigger and bigger. So collisions are a gradual but necessary part, if you like, of forming the solar system in the first place. Once you have planets, then we see evidence of impacts by craters. So this is the surface of the moon, and pretty much everything you can see on the surface of the moon is caused by impacts. You're not really seeing volcanic features, there are no water features, there's no wind, there's no atmosphere there, so nothing exciting is happening in that sense. The moon is dead, dull, and lifeless, and boring. It's like Dundee. I think it's something else. Probably anything else. Probably can't if I can say Newport, because no one likes Newport, but I don't know. Okay, so nothing really happens there now. There's no exciting geology. Earth is active and dynamic. We have winds, we have oceans, atmospheres, volcanic activity, plate tectonics, earthquakes, all sorts of cool stuff. Nothing happens on the moon, apart from other things crash into it and leave these holes, these craters. When we look around the solar system, there are some really big craters. So we're just going to look at the top sort of 3 or 4 now. So this kind of yellowy-orange feature you can see here is a thing called the Caloris Basin on Mercury. So Mercury is the inner planet in the solar system. It's the last thing that things can hit as they fall towards the sun. So it's kind of at the very bottom of the shooting gallery with all these rocks falling in towards the sun, because the sun is the most massive object in the solar system. It pulls all that stuff towards it. This thing is 1,500 kilometers, 1,000 miles across. It's a huge structure. And it's about 2 kilometers, just over a mile deep. I'll switch currency so that everybody hopefully understands how big and how deep these things are. And you can see very clearly that the geology is different. The colours are showing you something about the types of rocks, okay? And you can see that within this sort of yellow circle here, there are some younger craters, these blue circles, because they sit on top of the crater. So the way you date a surface, the way you work out how old a piece of the solar system is what sits on top of what. So how battered is the surface? It's kind of like people. The more battered and beaten up they look, the older they tend to be. That's not always true if you took the boxers, but in general, the lovely, fresh-faced young people don't have all these craters on them. You see what I mean, yeah? So the older a surface is, the more craters it's going to have stacked on top of it. So craters are useful. We call them chronometers. They're ways of estimating how old a surface is. So when you're looking at a solid surface, whether it's rock or ice, it gives us a sense of how old that surface is. We can kind of put an age on these things. The next big crater is bigger again, 2,300 kilometers. This is a huge structure on Mars. So it's this feature down here in the bottom right-hand corner. It's 7 kilometers deep. You could pretty much put Mount Everest in this, and it would almost be completely immersed inside this thing. So this is 4 miles deep, this crater. It's a huge structure. At the very bottom of that structure, there may be conditions where water could exist on the surface. You could have puddles for short periods of time, because it's deep enough, there's enough thin atmosphere above it that it could actually have the conditions for liquid water to exist. Mars is an amazing place. We're going to learn a lot more about Mars in the next few years with all sorts of missions going there and rovers on the surface. But just looking at the craters, you can see the southern hemisphere, this bottom half of the image, is covered in craters. But look at the top half, the blue bit. This isn't water, this is showing you height. Blue is low altitude, yellow and orange is high altitude, high ground. There's hardly any craters up here at all. that suggests it's young, right? Battered surfaces are old, fresh surfaces, uncollected surfaces are young. So the northern hemisphere of Mars is young, and the southern hemisphere is very, very old. Some people suggest this entire northern hemisphere is a crater, that something hit the top of Mars and blew the skin off. And then what we're looking at there is basically all that blue. If you imagine kind of wrapping it around the globe, that forms an almost circular shape. So maybe the whole northern hemisphere of Mars is a gigantic crater, but that's still an unproven theory. The biggest crater that we know about is actually very close to us, and it's on the southern pole, the south pole of the moon. It's kind of hard to see because it's very, very old, but it's about 2,500 kilometers in diameter. It's this kind of grey circle you can see here. And again, it's not obvious because there are lots and lots of other craters sitting on top of it now. But geologists have looked at this area and they've realised that there is a huge structure around here which is 13 kilometres deep. That's deeper than the deepest part of the oceans on the Earth. So these are enormous structures. These are huge craters. And this would have had a devastating effect on the moon after the moon had been formed, but obviously not quite enough to blow it to pieces. So where else in the solar system can we find evidence of impacts? We've already looked at Mercury, okay, the closest planet to the Sun, the inner planet in the solar system, and we've seen it has some big craters like the Caloris Basin. But there's a problem with Mercury. It doesn't seem to have a skin. So the crust of Mercury, the rocky outer skin that we have on the Earth, seems to be missing, or at least a lot of it seems to be missing. So side by side here, these two wedges, the left-hand one is a section through the Earth. Okay, so we have the crust at the top, a very, very thin layer of cold rocks that we live on. Then you have the upper and lower mantle, kind of plasticky rocks that kind of move around very slowly. Then you have the liquid outer iron core and the solid inner core, right? The iron balls at the centre, if you like. So we have a crust, a mantle, and a core in those kind of proportions. Now we have a lot more evidence on Mercury. We can get an idea of what it's made of. We've always known Mercury was a bit of an odd planet, very, very dense, which suggested its iron core was very thick, but we didn't quite know how thick until a couple of years ago. And it now turns out that the iron core is almost all the planet, like 85% of the volume of the planet Mercury is core, is iron. You look at the Earth, it's more like 50-60%. So there's a lot more iron inside Mercury compared to the other planets in the solar system that we can study this way. Those are side by side showing them to be equivalent. But look, it's the mantle and the crust is where the problem is. There's pretty much no mantle at all. Whereas the Earth has a lot of mantle, Mercury has practically nothing. Put them side by side to real scale, you'll see Mercury is really small. But it makes it obvious that the core is huge. So Mercury is a huge ball of iron with a little thin layer of rock on the outside. And so something has happened. Something has removed the rock. There should be a lot more rock on top of this. And one of the arguments is that maybe something hit Mercury when it was very young and basically blew the mantle away. And what we're seeing now is just a very outer bit of rocky mantle. The bit that was just around the core. That's all that survived. So maybe Mercury was once a much bigger planet that had basically had its skin ripped off, had its surface ripped off to a very great depth. If we come out to the next planet, Venus, we now have a very odd planet. And we've known about Venus being odd for about 20 or 30 years now, because measurements showed that Venus was very hot. So we know it's a very unusual, it's not a place where life could exist. People used to think it was going to be a tropical version of the Earth because it's a little bit closer, but basically the same size, has an atmosphere, all that kind of stuff. But some of the interesting things about Venus that we discovered were that it rotates backwards. So if you imagine looking down on the top of the Sun, on the north pole of the Sun, all the planets go around anti-clockwise, yeah? But they orbit in an anti-clockwise direction and they spin in the same direction. So they're kind of going around looping in this way. You'll see the Earth spins, tipped over a little bit, spins, and it moves in its direction. Mercury doesn't. Sorry, Venus doesn't. Venus moves anti-clockwise, but it spins really slowly in the opposite direction. Another way of thinking about it is that Venus is upside down. You can imagine taking hold of the arrows on Venus and flipping it the other way up. It would now spin in the same direction as Mercury and the Earth. The other problem is Venus's rotation is really slow. Earth spins once in 24 hours, one day. It takes 243 days for Venus to spin once around. A day on Venus is longer than a year being how long it takes to go all the way around. So birthdays on Venus would be a real mess, because you would be more years old than you were days old. It would get very complicated. And the idea there is that something hit Venus and literally spun the whole thing upside down. You don't have to actually hit the planet, you just come very close to it. The gravity of another planet passing nearby would be enough to pull Venus over. Yeah? So we think Venus has been flipped upside down somehow. So it's basically spinning on its top. We jump over a few planets now. We get to Uranus, one of the outer gas giants in the solar system. In Uranus, we find something very similar, but to an even greater extreme. It's not spinning upside down; it's spinning on its side. So these diagrams show you the axial tilt. So imagine the North Pole and the South Pole of the planet, and they spin around that axis. The North Pole and the South Pole of the Sun. So if the North and the South Pole of the Sun line up perfectly with the North and South Pole of the planet is parallel to the Sun. Yeah, it's spinning the same way. It has zero inclination. As you tip it over, the angle increases. So the Earth is spinning about 23 degrees. Yeah? You can see the Earth here, 23.5 degrees. So it's tipped over a little bit compared to the Sun. Jupiter, almost straight up. Yeah? Only a 3-degree tilt, pretty much parallel with the Sun. Saturn, 27 degrees. Neptune, 30 degrees. So these are all pretty similar values. So a bit of a tilt seems to be normal. And then you get to Uranus, and the tilt is 98 degrees. So it's not a little bit, it's not 20 degrees, it is all the way over on its side. Not Venus, upside down. I'll do this as a dance one day. But it's right on, it's rolling around the Sun on its side. So that's a bit odd. And again, this is a much bigger planet now. You're looking at something which is much bigger than Venus. So rolling it over takes a lot more energy, a lot more mass to do that. And now that we know that Uranus has moons and also has little tiny rings around it, we find that they're all tipped over as well. So these are images taken by the Voyager mission and by the Hubble Space Telescope. You can see some of the moons of Uranus here and these very thin rings that it has. So all of those structures are tipped up on their side as well. So Uranus is on its side, Venus is upside down, Mercury is missing its skin. These are very odd things in the solar system. And the one thing, the one idea, the one model that we have in common for them is that something hit them. So I always tell my students, if we don't understand something in astronomy, we have two basic explanations. Either something hit it, or it's magnetic fields. Because we don't really understand magnetic fields, and they can do all sorts of magical things. So we just have two great explanations. Yeah, it's just, or it's quantum stuff, something weird to do with quantum physics. And we can explain pretty much, well, we can not explain pretty much everything that way, but it's kind of it's a nice excuse. But in this case, it sort of works, right? Impacts the things we understand. You ever walk into somebody or into something, you know what it feels like. You know that there's an energy transfer. You stop moving and the wall wasn't moving in the first place. You bounce off. You recoil. There's an energy transfer between you and the thing that you hit. So we're going to look now briefly at impacts with the Earth. The Earth and the Moon are very close together, so essentially they're the same place in the solar system. The Moon's surface is absolutely battered. Like I said, there's nothing else happening on the Moon really apart from things are hitting it. But the Moon and the Earth are very different, not only in size, but also in the fact that they differ in their structure, but also the fact that the Earth has an atmosphere and active geology. But we think an impact actually created the Moon in the first place. So this is an artist's impression of this big grey ball coming in from the top left corner here. We call this Thea. It's even got a name. It's a theoretical mini planet. It was about the size of Mars, we think. It smashed into the proto-Earth, the newborn Earth, just after it was created. So within the first few tens of millions of years of that big cloud collapsing and forming the Sun and all that other stuff. And the impact, this giant, horrible game of pool or billiards or whatever, everything smashing into each other, meant that the iron that was in the centre of that mini planet, in the centre of Thea, sank into the Earth. So the Earth absorbed the iron, and we got a bigger iron core, and that's a good thing for us. The rocky material from the outer skin, the rocky outer surface of Thea, was blown outwards. It was trapped in orbit around the Earth, and eventually, in maybe 1 million years or so, that material came together, this bottom-up process, little grains getting bigger and bigger and bigger and bigger, until eventually they created the Moon. So an impact very early on in the solar system gave the Earth a bigger iron core. Now the iron core makes our magnetic field. The magnetic field protects us from the Sun, from radiation from the Sun. So that's a good thing. So that was a good consequence of the impact. The other good thing is that the Moon is big. It's about 1/4 of the size of the Earth. It's a stabilizer. Okay? It stops the Earth wobbling around too much. So Venus has been flipped upside down and Uranus has been tipped on its side. A similar fate didn't happen to the Earth because we had a moon. So if we did start to wobble, the moon's gravity would kind of pull us back again. So we think that having the moon as a stabilizer was a good thing because it allowed Earth to be stable. It allowed us not to be wobbling around and life on Earth being killed by all these weird things happening. So having a moon is a good thing. So this was a good impact. Any life on Earth at this point, there wouldn't have been. But if anything had been alive there, the whole surface was effectively destroyed, melted, so it would have wiped it out. So if it happens now, it's a bad thing. Because it happened a long time ago, it's a good thing. A couple of years ago, so 2.5 years ago now, I'm sure you remember this event. This was this Chelyabinsk meteor. So I've got some little video clips. You've probably seen these before, but they're quite interesting. This is a small object, 18 meters in diameter, something that would have fitted in not much more space than this room. And yet the footage from all these paranoid Russians filming everybody in case they get insurance fraud claims, you see this object burning through the sky. Now, nearly all the injuries, about 2,000 people were hospitalised. Nobody was hit by anything from the meteorite. It was glass from windows, because they saw the flash of light, they walked over to the windows, they saw this amazing trail in the sky, and about 90 seconds after the light flash had reached them, the blast wave, the sound wave hit them and blew all the windows out of their faces. It tells you that light travels a lot faster than sound, right? This is the sort of thunder and lightning thing. But you can see this was an incredibly dramatic event. And it was captured by thousands, well, hundreds of cameras, security cameras, dashboard cameras. So the measurements that we have of that object coming through the atmosphere are incredible. And this is why the most dramatic. And you imagine the poor driver of this thing just seeing this ball of light appearing over his head. This is sort of 9 o'clock in the morning or something. Here is radio playing in the background. And that was a small object. But the odd thing about this was that nobody saw this coming. Literally no one saw this coming until it hit us. And you can see, very dramatic. There was another one in Thailand, actually, a couple of days ago. There's a lot of YouTube footage at the moment showing something not quite as dramatic as this, but still very similar, over Thailand. So these things do happen. And what was falling down out of the sky underneath that trail of rock, that trail of smoke you can see effectively, were meteorites. And because it was relatively snowy, you'll see snow on the ground there, people were finding little holes in the snow, and at the bottom, little fragments of meteorites. So lots of meteorites were recovered from underneath where this object had passed through the atmosphere. It didn't hit the ground, it blew up kilometers above the surface. Because the rock itself was quite weak, the pressure of pushing its way through the air was kind of building up in front of it and exerting pressure, meant that the rock exploded. So at the very end, you'll see the object actually gets very bright and then it fades away. Yeah, you'll see that kind of it dims. At the point at which it's very bright, that's where the pressure of the atmosphere is enough to break the thing to pieces. And what was found in the end was one big lump, about 100 kilos, so a lump of rock about this big, that had landed in a lake. But the rest of the thing, we think it would have weighed maybe, 5 to 10,000 tons, is gone, it's disappeared. It was broken up in the atmosphere, turned into dust, and what we've recovered is a few hundred kilos of the object, which would have weighed 10,000 tons probably in the first place. So lots of evidence of this object and what it was like. Right, let's go back over here. So here's what we think Chelyabinsk was like. About 17, 18 meters in diameter, so 20 yards across, roughly 10,000 tons in mass, so the mass of a decent-sized ship, basically, and it released as much energy as 500 kilotons, 500,000 tons of dynamite. The energies that we would use, the units of energy in joules and things like that, we don't bother with those, because when we're dealing with these sorts of objects, they're moving so fast and they're so massive that they deliver the sort of energy that a nuclear warhead would deliver. So we talk about megatons, millions of tons of dynamite, or in this case, kilotons, thousands of tons of dynamite. And you'll see that the Chelyabinsk meteor, as it was called, is relatively small compared to some of the others here. This is, on the left of this greyish, or sort of brownish object, is the Barringer Crater meteor. This is about 50 meters in diameter, but this was iron. So not just a loose, sort of weak rock that we think Chelyabinsk was, but a big lump of iron, basically a bullet. These things travel much faster than bullets. So not only are they the size of buildings or mountains, these things are traveling way faster than a bullet. A bullet is typically 2 or 3 kilometers per second, so a couple of miles per second. About the speed that Flyby flew me up here this morning, probably. So because they have so much velocity, they're traveling so quickly, these things are traveling at least 11 kilometers per second. That's the speed that things fall from space. So if you take something to space and drop it to the Earth's surface, it should hit the ground at about 11 kilometers per second, give or take. That's 5 times faster than a bullet fired from a gun. Now, some of these things have been clocked at up to 72 kilometers per second. So that's 30-something times faster than a bullet. These things are really, really quick moving. This is why the Rosetta mission that I showed videos of at the beginning, I'll talk a bit about later, was incredible, to catch up with a comet flying through the solar system at 60 kilometers per second. It's a phenomenal speed. Just to get out there, we have to use the gravity of several planets to get our space probe faster and faster and faster. So, things hit us. They can be massive, but they're very fast. And it's that combination of speed and mass that makes these things so dangerous. But these are human scale, right? You can see these are compared to the size of a Boeing 747 or your average Ticonderoga class cruiser, which I'm sure we're all familiar with. These are human scale. You could see one of these things. But the biggest objects that hit us, the mountains that fall out of the sky, the things that cause mass extinctions, those are kilometer scale. Those are things that are the size of a mountain, Mount Everest scale. So this happy little graph is death against time, or life against time, depending on whether you're being positive or not. So on the right-hand side, on this lower axis, here we have time. Okay, so 0 is today, then 200, 400, 600 million years ago. The solar system, quick, if you want to remember how old the solar system is, nice easy number, it's 4.567 billion years. See, some geologists are saying that's an age now. They're like, no, don't want the age, because that's easy to remember. But that's the age of the solar system, 4.567 billion years old, right? 4,567 million years old. We can measure that because we can look at rock samples and we can age them, we can date them. So this is only looking back 600 million years. If you it's like going all the way back to the beginning of the solar system, it would go out through that wall somewhere, quite a long way. So we're only looking at the last bit of the age of the solar system, like the last 600 million years. And that's a period of time where life comes from the oceans onto the land. So that's an interesting time for us. Going at the top here, the y-axis, is the number of families. I'm not a biologist, but basically like the primate families. Monkeys, gorillas, humans, right? We're all the primate family, the bird family, canine family, that kind of thing, roughly. And you'll see that this is for land animals, yeah? And it starts off at 0, the bottom left corner here, and it goes up to the top right-hand corner at about 1,100 families, something like that. So it's gone up over time, which is good. But it doesn't go up in a nice straight line. It doesn't just start at the bottom and just diagonally shoot across the diagram. It goes up really sharply, and then it comes down. When it comes down, that means families are being destroyed. So if you imagine killing every single primate, human, monkey, gorilla, ape, every one of those creatures on Earth, wiping them all out, that would drop it by 1. You wouldn't even notice on this diagram, yeah? So when it falls here, for example, by maybe 100, that's a lot of death and destruction on the Earth. Something dramatic is happening to life on Earth. Then you go along, and you get this big drop at about 450 million years, this big vertical drop, the first one. Then it goes up again, and it goes down a bit. There's a big one here, and there's a big one, or biggish one here. In total, we think there are about 6 of these so-called mass extinctions in the last 600 million years. The most exciting for us, in a sense, is this one. This is the end of the Cretaceous. This is the Dinosaur Killer. So the dinosaurs ruled the Earth between about 210 million years ago and about 65 million years ago. They were the kind of dominant form of life on the land. So there's T-Rex and all his pals wandering around, eating everything else. But they were wiped out, and the end of that diagram, where it shoots up, is where the mammals take over, and ultimately us. So life on Earth was very different in the past. And it changed when these events happened. They changed life on Earth dramatically. They changed the weather, the climate so dramatically that life on Earth was fundamentally different. And we don't know what happened at these times. What we think is that there are craters, holes in the ground, that line up with nearly all of these mass extinction events. So we think something hit the Earth, threw up dust into the atmosphere, made the Earth very cold, and killed lots of life on Earth. It changed life on Earth because of the weather changes, if you like. The only one we don't have a crater for at the moment is this big one here. This is the one, it marks the Permian and the Triassic, 250 million years ago, that big drop in the middle. They call it the Great Dying. Geologists are not excited at coming up with names thing. So the Great Dying is the biggest mass extinction on Earth, right, that we've ever seen. It might go even deeper than that diagram shows. It's hard to quantify these things. But recently, geologists think they found 2 craters, huge craters under Australia. So we blame it on the Australians, right? But they're very deep, and they're 2 side by side. So it may have been an object that broke into 2 pieces just as it hit the Earth. It's unlikely that 2 objects hit at different times. It's much more likely that one object split just before impact and created two craters. And we see this in other parts of the Earth and other parts of the solar system. So bearing in mind that the Moon is covered in craters, you'd expect the Earth to be even more covered in craters. We're bigger, we're more massive, we pull this stuff in from the solar system. But actually we don't find many craters at all because the Earth has all this stuff going on. You know, the Earth has oceans and atmospheres and plate tectonics. It hides craters very efficiently. Even the craters produced by these mountains falling out of the skies. This is an artist's impression of a giant space rock coming out of the sky, hitting the Earth, and just at the point at which it's about to be destroyed, because as the object hits the ground, a shockwave blows backwards and rips the object to pieces. So the object isn't buried in the ground underneath. You don't dig a hole in a crater and find a big space rock underneath there. The object is pulverized, it's smashed to smithereens, and those smithereens become meteorite fragments. It blows a huge hole in the ground when it hits the surface. Before it hits the ground, it pushes the air in front of it and heats it up. So this kind of white stuff you can see flowing out to the side is meant to represent a shock wave. A wind of 600 to 1,000 kilometers an hour. So way, way beyond hurricane winds. But also probably heated up to maybe 1,000 degrees Celsius. So you're incinerated by a hot wind, you're blown to pieces by the wind itself, you're hit on the head by rock fragments, you're melted by rock, all sorts of bad things happen to you. You don't want to be anywhere near one of these events. If we look at a map of the Earth and we put the craters on, we find something a little bit odd. You'll see some parts of the Earth, like North America and Canada and Australia, have loads of craters. Yeah, the size of the crater is indicated by the size of the circle. If it's red, it's on the surface. If it's orange, it means it's under the ground. It's subsurface. So we only find it if we look beneath the surface. South America looks relatively unscathed. North America looks battered. Africa looks relatively unscathed. But look at the Baltic. Look at sort of the Baltic states, Estonia, Latvia, that kind of thing. It's absolutely covered in craters. Now there are two things in effect here. One is the age of the rocks. The older the rocks, the more battered they are, the more craters they'll have. Yeah. So if you look at ancient rocks like North America and Canada and Australia, you'll find more craters anyway. So that's one selection effect. The other one is where the scientists are and what they're interested in. So North America and Canada, lots of geologists and astronomers interested in craters. They find lots. Same in Australia, lots of interest in geology. They find lots of craters. South America, jungle, nasty, bitey spiders and stuff. No one bothers looking for craters in the jungle, in the Amazon, because it's far too dangerous. The same with lots of Africa. You've got deserts, you've got jungles. It's not good terrain to be wandering around with a hammer looking for strange bits of rock and holes in the ground. The odd bit is Latvia and Estonia. But it turns out that the selection of it there is that scientists realised that because they had no money to do experiments and build telescopes, one cheap bit of science they could do was to go out as geologists and look for craters. So they just went out and found loads of little ones. So you had that big concentration of red dots around the Baltic up there. But you'll see that there are huge areas of the Earth with no craters, the oceans. The oceans are very young. The rocks under the sea are very, very young. Tens, hundreds of millions of years old, and that's it. Compared to the rocks of North America and say, South Africa and Australia, which could be billions of years old. Older rocks, more craters. Younger rocks, like the oceans, hardly any. There's only one crater just up here, which is in the ocean, under the sea. The other one we're going to look at is this one, which is Chicxulub. This is the one we think killed the dinosaurs. And that's kind of half in the land, half in the sea. This is probably the most famous crater on Earth. It's called Meteor Crater. It's not a meteor. A meteor is a sand grain-sized object that burns up in the atmosphere. Friction just basically melts the thing. This was made by a lump of iron about 50 meters in diameter, I showed you a little bit earlier. It happened about 50,000 years ago. We know it was iron because there are iron fragments of this thing scattered. The meteorites that you find are all iron, little tiny bits of iron. You walk around here still today with a metal detector and it goes crazy because there's so much iron dust, if you like, in the ground here. And it's been very well preserved because it's in Arizona, it's nice and dry. And now you can pay $15, you can drive up that little road at the top right there, and you can park up in the big car park and go into the museum and pay $15 to look at a hole in the ground. I took my kids there about 3 or 4 years ago when they were kind of in their mid-teens, and they were very unimpressed. I was like, look at this! They were like, it's a hole in the ground. I was like, yeah, but it's an impact crater. But it didn't work. Well, we'll wait for the DVD to come out. It'll be on YouTube one day. But when you get there, the scale of this thing is huge. You can put a 60-story building in the centre, and it won't pop out over the rim. You can't really get a sense of how big this is until you stand there and realise all of this rock that was once there is now scattered and blown for miles in all directions. If you look at that crater in a different type of light, that's an optical picture, right? What our eyes can see. This is an infrared image looking down on the crater from above, and it shows you differences in the geology and the rock types. And what you notice here, the crater is very obvious. You can see the kind of green patch of the lowest regions of the rock. You can see the rows and things. But look at the red. It's all kind of pointing off in the sort of right-hand side, isn't it? And the suggestion now is that the meteorite that came in, smashed in, came in from this direction, and the material was blown out of the crater in the opposite direction. Like it kind of carried on going in that direction. So in the infrared, if we take images in different forms of light, infrared is what this laser is. This is an infrared laser. It's the same sort of thing you use to change your TV channels and stuff like that. Infrared light shows us the direction that we think the material went, so the direction that we think the object came in at. This is a crater in Quebec, in Canada. It's about 100 times bigger than the last one we were looking at, the Meteor Crater. It's about the same age as the little mass extinction that started the dinosaurs. So this could be the scar on the Earth that caused the life on Earth to change and for the dinosaurs to then take over, because they were brought in by a mass extinction and taken out by a mass extinction. Chunks of rock from Canada, from Quebec, have been found in Bristol. Yeah, Bristol's thousands of miles away. I know because it takes me 7 hours to get to Aberdeen from Bristol in an aeroplane, so it must be far away. But, okay, the Earth was everything was closer together when this happened. This is 210 million years ago. But even so, rocks from there were blasted thousands of kilometers and have been found in rock layers in the southwest of England. So this is a big event. The original crater was even bigger than this. This is now a lake. What you're seeing here is erosion. The ice has come and gone back and forth and rubbed away the rocks. So the rim of the crater is gone. You're only seeing, effectively, the bottom. The inner there's a bump in the middle and a kind of a flat bit around it. So over time, most of the crater has been eroded away, and what's left has formed kind of a moat around the central bump. The original crater was probably about twice the size of this, so we think it might have gone out this sort of region out here. Again, there's a little bit of change in the geology, but nothing too obvious. So we do see craters, and again, if you take satellite images, you see more and more strange features on the Earth. Some of them half on the land, half in the sea. Some of them in mountain ranges, so they're all kind of twisted and mangled. This one is below tens of meters of sand. So it was found by effectively a ground-penetrating radar system that was used looking for oil fields. Most of these things are found by oil companies, which in Aberdeen is probably quite appropriate. You understand this a lot better than most people in the UK. But oil prospectors use various techniques like ground-penetrating, gravity measurements and magnetic measurements to see below the surface. So we can see the buried structures where the oil is, but also we start to see structures that are now buried below deserts and even below jungles and things. One of the biggest structures that we found on Earth is very old. So this is about, you see how well it's been dated, 2,023 million years old, plus or minus 4 million. We have a really accurate date for this. I mean, if I said to you I'm 40-ish plus or minus 4 million years, you'd think I was being a little bit vague with my dating. But 4 million years for an object for a rock this old is very accurate. It's been studied in great detail. It's the second oldest crater on the Earth, but all that's left of it is this kind of arc of mountains. Yeah, in South Africa, that's all that's left. The rest of the crater is basically being destroyed and eroded over time. But bear in mind that when I mentioned at the beginning that we think we found the evidence for in Scotland that the rocks that were once part of this object that got destroyed, that was 1.2 billion years old, 1,200. So not quite as old as this, but not far off. Okay, what hits us? Well, there's two flavors of stuff that can hit us, really. Asteroids and comets. We'll just briefly look at what these two are. Asteroids are lumps of rock and metal. That's kind of what you were holding, right? You were holding pieces of asteroid, the rocks and the metals, the meteorite samples that we've got. Most of them, 95% of these objects, live in what we call the main asteroid belt, and that's between Mars and Jupiter. Okay, it's a long way from us, it's not a problem. It's the few percent, a couple in every 100 that come towards the Earth that are a problem. Now, a couple of percent doesn't sound like much until you realize that there are millions of these objects, and a couple of percent represents 10,000 objects that come close enough to the Earth that we worry about them. We've flown space probes around them, we've taken pictures of them. They're dull, grey-ish, potato-shaped lumps of rock. There is no interesting geology on these things. Some of them, like this one, look like piles of rubble. This is only about 300 meters from end to end. Okay, it's a very loose pile of rubble, and the smooth bits you can see, for example, this top left bit here, are dust. So this is basically a gravel pile flying through the solar system. The one on the right-hand side is 30 kilometers end to end, and it has a little moon. This is Ida, the big object, and Dactyl, this little thing here, is a 1 kilometer moon that orbits around it. So it's not just planets that have moons, asteroids can as well. And objects like this one may actually be two asteroids that have kind of come together, a little bit like we'll see in a minute with Comet 67P, where the things have kind of touched each other and stuck. We've flown around and imaged lots of asteroids, and they're all basically dull, potato-shaped lumps of rock. They have slightly different geologies, and that's reflected in meteorites. The biggest one we've observed was actually this one, Meteor, this huge thing in the middle. It's 132 kilometers. And you can see that pretty much the only stuff that you can see on the surface is craters. The only thing that happens to these objects is that stuff hits them. They hit each other and knock lumps out of each other and form craters. So craters are very, very common throughout the solar system. And you've seen some meteorites. These are some examples of very pretty polished sections and things. But these are all bits of asteroids. They're all the bits of asteroids that have survived passage through the atmosphere and landed on the Earth's surface. Imagine two of these lumps of rock and metal flying through the solar system, collide with each other at huge speeds, smash each other to pieces. If the objects are big enough, they have an iron core and a rocky exterior, and a bit in between, which is a little bit of rock and a little bit of iron. And so the three main classes of meteorites are iron, top right, which is from the core, stony, these two at the bottom here, which are the crust, the outer part of these asteroids, And then rarely you find this material called a stony iron. Again, geologists aren't great at coming up with exciting names, right? If everything dies, it's the great dying. If it's made of stone, it's called a stone. If it's made of iron, it's called an iron. If it's made of a bit of both, it's called a stony iron. Stony irons are very pretty, though, but they're very fragile. They crumble and fall apart very easily. But they make beautiful, you can make earrings and stuff out of it, apparently. And you backlight them and you get these lovely crystals, these olivine crystals that we find deep in the Earth's surface, but here they're exposed after this giant collision. So this is where the classes of meteorites are created, depending on which bit of rock or metal has been thrown out in the explosion. If you look at a textbook, it'll say, right, asteroids live between Mars and Jupiter, and that's fine, and we're safe, and that's kind of what your classical diagram looks like. This is a plot showing about 500,000 real asteroids. It's about 10 years old now. I should update this at some point. But it makes the point. The big outer circle is Jupiter. The inner circle you can just about see between the red and the green is Mars's orbit, so the Earth is the next one in. All the green dots, and there's roughly 500,000 of them, those are main belt asteroids. They just go round and round between Mars and Jupiter. They're no problem to anyone. Unless you happen to want to fly from Earth to Jupiter, you've got to go through all this, but there's huge amounts of empty space. The red dots are ones that come close to the Earth at some point. Now, again, I should define this. When I say things are relatively young, I mean 1 million years. When something comes quite close to the Earth, I mean 3 million kilometres. So roughly 10 times the Earth-Moon distance. That has me panicking and diving under a table. I get panicked very easily, obviously. But within 3 million kilometres, that's something where in the future its orbit might change a little bit and it might come back and it might hit us. So all those red dots, even the ones way out on the edge here, you see this one at the very top up here, for example, right up here, you think, well, how can that be a threat to the Earth? Well, its orbit comes all the way down round the Sun and back out again. So this thing lurks out in the dark for a long time, and every now and then it kind of reappears, then whooshes out again. So sometimes we don't see these things coming, like the Chelyabinsk meteorite. We didn't see it coming because it came from the direction of the Sun. Astronomers notoriously look up into the sky at night, so anything coming from the Sun is effectively coming from behind us, and we don't see it coming, right? It's it's behind you type setup. But there are roughly 5,000 objects on that diagram which are threatening to the Earth that we kind of have to worry about. So, one of the projects I run is a thing called the Faulkes Telescope Project. And we were talking to some of the students here today, and we're hoping to get the schools in this area involved in this. We have telescopes around the world, which are remote controlled over the internet. Imagine like a giant video camera or still camera, but 10,000 kilometers or whatever mounted. And we take pictures. You do that all over the internet. So you get to use a professional 2-meter telescope, so a big telescope, and you get to take images. So this is an image that was taken about 7 or 8 years ago of a bit of sky, and we told the school there will be an asteroid in this bit of sky. So they went and took a picture, and they sort of went, well, we can't tell which one it is, because there's just some fuzzy white blobs on a back, Is the asteroid this big blob here, or this little tiny faint thing, or it could be anything, you have no idea. So we have a couple of tricks that we use. The first one is we negative the image. We make black, white, and white, black. And your eye now is a little bit better. You can see the fainter things a little bit more easily than you could before. Yeah? So that's the first thing. The second trick is, okay, well, most of these objects are stars. They're really, really far away from us. Tens, hundreds, thousands of light years. So effectively, they're fixed on the sky. They don't move. The asteroids are much closer. They're only millions of kilometers away. So they move quite quickly in comparison to how slowly the stars, which are far away, move. So if we take a sequence of images, we take an image. 5 minutes later, we take another image. 5 minutes after that, we take a third image, all pointing exactly the same part of the sky. And then we just blink one after the other. Show image 1, image 2, image 3. So that's what will happen next. You'll see 3 images, 1, 2, 3, bottom left-hand corner. And the asteroid will jump from one image to the next because it's moving. The stars will be fixed. So you're looking for the jumping object. Can everyone see towards 12 o'clock on a clock face? That jumping object up there? So that is the asteroid that we knew was there. So the school successfully found an asteroid that we already knew about. And they said, oh, well, we found the other one. We said, what do you mean the other one? There's one there, we told you. They said, no, we found the other one as well. Anyone see a second object moving in that image? It's kind of hard to see.
3 o'clock.
Yeah? Yeah, exactly right, about 3 o'clock. So just above this bright star here, you see this little fuzzy blob. I'll zoom in there. Really hard to see. That was a discovery. We accidentally discovered a new asteroid whilst looking at the asteroid belt where most of them live, so it's kind of cheating a little bit. But because we're using a big telescope, most people only look at with little telescopes at the asteroids because they're not very interesting to most people, we accidentally discovered a new asteroid by looking at one that we knew was already there. So you actually kind of find these things. You get to name them. There are all sorts of rules. You can't name it after a politician or a military leader from the last 100 years. You can't name it after a swear word, and they check Welsh and Swahili and all that kind of stuff. But other than that, so there's a John, Paul, George and Ringo. There are 4 asteroids named after the Beatles. There'll probably be a Justin Bieber one day, but they're named after scientists and all sorts of things. You can make videos of these things moving. So this was a group of teachers that made a video. So these teachers here all got together, they made a video. You see 2 asteroids moving through the sky, a bright one and a fainter one. They're totally unrelated, they just happen to be in the same patch of the sky, moving near each other. That fuzzy blob here, by the way, is a galaxy, really, really far away. So stars, stuff in the solar system, stuff in the galaxy, and stuff in another galaxy. And what these teachers and their students did was they measured the brightness of that lower blob, and they plotted it against time, and that's what this diagram is over here. So this is time from 10 o'clock to 50 to 3 o'clock, so this is going 5 hours. And the lower down the points are, the brighter the object is, and the higher up, the fainter. So this thing was bright, faint, bright, faint, bright, faint, bright, faint, and so on and so on. They were able to measure the rotation of the asteroid. So if you imagine this is your asteroid, this one happens to have a shiny bit on one side. So you're seeing the light that's being reflected off the projectors and the other lights in the room. Yeah? So it starts off here, it rotates, and that shiny bit, which bounces lots of light towards you, so it looks bright, disappears, and you just see it end on. So it's really faint now. Then you see the back. Well, it's dark, but it's quite big, so it looks a bit brighter. Then it rotates again, really small and dark, really faint, and then it comes back again. So this is the first bright patch, and then that's the back side of the object, and then this is the second time you see it. So the distance between here and here, which is about 3 hours, is how long it takes this lump of rock to spin once around. So this school could make scientific measurements using our telescopes by observing this. And they made a nice little movie, and they made some measurements of an object that is tens of millions of kilometers away. So this is schools doing real science, real stuff that can be useful to scientists to figure out how fast these things are. There's another one. So, and this one, it gets fainter as this is upside down. So it's faint, bright, faint, bright, faint, bright. And you can see what's going to happen. It's going to repeat this over and over and over again. So we can measure very accurately how slowly or how quickly these asteroids are rotating and tumbling through space. That's what I want to mention, because I know this is oil town, as it were, and so how much things worth are probably quite important. People talk about mining asteroids. You say, well, that's insanely expensive. It'll cost billions to go to the moon. So going to asteroids, tens of billions of dollars to do that. So I gave a talk in the City of London in 2010. So I thought, well, what will interest... They said, oh, it's going to be like bankers, and well, oh, great, that's my kind of audience. I thought I'd talk about money, how much these things are worth, to try and convince them that space is worth money. So there's an asteroid called 1986 DA. It's 2 kilometers. It's a lump of iron, about 2 kilometers across. It's a flying lump of iron, basically. About 8% of it we think is nickel. The rest is pretty much iron, but other stuff mixed in. So I thought, okay, let's work out, in January 2010 prices, how much this asteroid was worth. So it turns out it's got about 10 million kilograms of gold inside it, we reckon. And that's worth $400 billion. Okay, 0.4 trillion. A trillion is 1,000 billion, 1,000 million. So it's worth $400 billion in gold alone. Then you have the iron, massive amount of most of this thing is iron, right? That's worth about $2 trillion. So already you're thinking, well, okay, if it's going to cost tens of billions, it's already worth $2.5 trillion. So it's your quid's in with this thing. Platinum, 100 million kilograms of platinum, $5.5 trillion worth. But the most valuable part of this is the nickel. The nickel is worth was in 2010, $17.6 trillion. So that whole thing is almost $26,000 billion worth. Of course, the problem is you bring that much gold and nickel to the Earth, you flood the market, right? People say, oh, there'll be diamonds the size of mountains out there, which is great, but diamonds are valuable because they're so rare. You bring a mountain-sized diamond to the Earth, De Beers go bankrupt instantly, and diamonds aren't worth anything because you've got loads of them. So it's a nice idea that diamonds will be worthless. I keep telling my wife that's why I didn't bother buying any. It doesn't seem to be working. Right, we'll finish off now. So what else is out there? Rock and metal, asteroids. And the other thing is comets. So we'll talk a little bit about Comet 67P and Rosetta in a minute. This is what you see when you see comets, these beautiful, ghostly-looking objects with these huge long tails behind them. And you kind of assume that this object is coming down here, and that this object is moving that way. I have no idea which way this thing is moving. This thing, I know, is going that way. The only thing you can tell from the tail is that it points away from the sun. Because basically, a wind blowing from the sun and the magnetic field of the sun push material off the comet. So the tail always points away from the sun. So as a comet's moving outwards, back out into the solar system, the tail is in front of it. Okay, so you can't tell. So this comet could be going to the right or to the left or up or down. I don't know. All I know is that the sun is over here somewhere, blowing its wind in that direction. All that material, all that white stuff you can see is basically snow. It's tiny little particles of snow. The tails can reach 1 million kilometers or so in length. They're huge. You could pack up nearly all the material into a couple of decent-sized suitcases. Ryanair would charge you millions of pounds to fly them, I'm sure, but it's not a huge mass of material. It's just very shiny. It's white, shiny material. Our model of a comet, this has changed a little bit now because of the Rosetta mission, which we'll see in a minute, but we assumed that these things were dirty snowballs, right? But now we think maybe they're snowy dirt balls. It's a bit of a mix of the two. So the inside is ice and rock, mostly ice, but with some rock. And the outside is this black crust, this very, very dark, crusty material, black carbon-rich material. So this is a huge iceberg covered in carbon. And in some ways, you can imagine human beings are carbon-based life forms with a lot of water in them. So, okay, I'm not saying we are like comets, but comets are kind of like us in a way. They have a lot of water, a lot of carbon, which is what we do. So people argue that these are fundamental to bringing the ingredients for life on Earth, not life itself. Some people think that. There's a very small minority of scientists that believe life may have come from comets. A theory called panspermia, but it's very fringe at the moment at least. But certainly the chemistry, like I say, the water that falls on us out of the sky regularly, I live in Wales, it happens all the time, most of that water, half that water maybe comes from these objects, from these comets. Right, I'm going to have a little break and show you a little video, because I'm sure you're fed up of hearing what's left of my voice. I'm going to play you another little, if I can make this go away. There's a nice video that was made by the European Space Agency, who, as Tim mentioned, I have to kind of promote, which was called Ambition, and it's all about the mission to Rosetta, the Rosetta mission to Comet 67P. Just watch this for a quick second, I'll let my voice recover. It features someone from Game of Thrones, so if you like Game of Thrones, you'll be happy with it. This is trying to encourage children to be interested in science, basically. This is what this is all about. So they use science fiction as a way to try and interest people. I'm just going to consume some comet juice while you're...
Enough. What was it? Perhaps we should find you something little less challenging.
I don't understand. I've done everything. Let me do it again.
Once upon a time.
Really?
This is a good one, I promise. What is the key to life on Earth?
Water.
Water. For a long time, the origins of water and indeed life on our home planet were an absolute mystery. So we began searching for answers beyond Earth. Where could all this water have come from? In time, we turned to comets. 1 trillion celestial balls of ice, dust, complex molecules left over from the birth of our solar system. Once thought of as messengers of doom and destruction, and yet so enchanting, we were to catch one. A staggeringly ambitious plan.
Are you talking about the Rosetta mission?
Throw me the probe.
The Rosetta is about 30 meters across. The solar panels are absolutely huge. So each solar panel would cover one of these rooms easily. So it's an enormous spacecraft.
things could have gone wrong. Failure at launch, an error in the calculations, collisions, so many unknowns. With the technology we had back then, we may as well have been shooting from a slingshot. Tell me, what was it all for?
Knowledge.
Yes, but we also wanted to show what was possible.
This is the Philae lander that was meant to touch down on the surface and do experiments, but kind of didn't quite work as they planned. It bounced a little bit.
I know of this from the archives. There were bigger missions after.
Yes, it was the first one to catch a comet. Ambition. Stubbornness. Nothing has changed. We fall, we pick ourselves up again, and we adapt. I was watching you earlier. You actually did everything right. I destroyed your rock. I needed to see how you'll react. You're ready. Reset. Nicely done. Let's begin.
So that was ESA's attempt to try and catch up with NASA. Everyone thinks NASA does space and nobody else does, but actually the European Space Agency does a lot of space stuff. It's just we're not very good at publicising it. That's not just my fault. That's ESA in general is quite quiet about what it does. So Rosetta was the first mission where they really went into town and tried to publicise what they were doing, because they figured people would be interested. This isn't about stars and galaxies and black holes and weird stuff. This is about figuring out where water comes from. And water is fundamental to life. So this is something that everyone can relate to. This is trying to figure out where water came from and maybe where the origins of life came from in the solar system. So they spent money on this. They made cartoons. They've done a lot of work just trying to promote this one particular mission. And the images that came through were initially very odd. This wasn't what they were expecting. All their models had this kind of lumpy, icy thing. And the first pictures that came through had this object which was very clearly two things that stuck together. So very rapidly, I think it was David Shipman, the BBC journalist, nicknamed it the rubber duck. And you can see why it has a head and a body. And as they got closer and closer and the images got better and better, they could see an incredible, and the images coming through now are showing objects on the surface that are, a foot across, 30 centimetres across. We get incredible high-resolution images. But this is not rock, this is ice. This is so black, the only thing comparable to this would be photocopier toner cartridge. It reflects about 1 or 2% of the light that hits it. It's blacker than black, if you like. Okay, it's blacker than coal. It's a very, very dark, icy material. We've got images now taken from all different angles. We can see strange, these sort of stripes that appear to be on the back of the head. This is looking at the duck's bottom, effectively, the back of its head. And you can see very, very weird things. All these, what look like craters, are not caused by impacts. We think that's where the ice is collapsing. So the icy material is being blown out by jets that form the tails that then stream along behind. And you'll see the faint glows that are coming out the back. As the comet gets closer to the sun, it heats up, and the ice starts to sublime. It goes from solid to gas. It doesn't melt, become a liquid. It goes straight to gas. And that gas gets blown off in jets. And there was a spectacular image a few months ago. This jet appeared, lasted for a few hours, then disappeared. It's like a geyser on Earth, like these jets of water you see in Yellowstone Park, something like that. And this is water. This is the snowy material being blasted out from inside the comet as it gets closer and closer to the sun. So we know a lot about comets now, far more than we did a year ago. So the last bit then, what is it that kills us? What is it that causes these mass extinctions? Because we have to link those two things, the asteroids and the comets, with the death and destruction. This diagram, how do we explain this? So what's going to happen is that one of these things, an asteroid or a comet, is going to fall from the sky at incredibly high speed. It's going to be big. It's going to be at least 1 kilometre. We think that's the minimum size to cause a mass extinction. The one that killed the dinosaurs was probably 10 kilometers, 5-6 miles across. It's going to hit the Earth with an incredible amount of kinetic energy, fast and massive. It's going to excavate, it's going to dig a hole, and it's going to throw the rocks out of that space. The hole itself, the initial hole, is roughly 20 times the size of the object. So if the object is 10 kilometers, the crater is 200 kilometers across, and probably about 40 or 50 kilometers deep. That's an enormous amount. That's about the size of Wales, right? That's a hole the size of Wales. I live in Wales. It's not quite that bad, but a hole the size of Wales is a huge thing. That material then goes up and out. So this artist's impression at the bottom here, this is on the cover of New Scientist magazine like 10 years ago. Someone who didn't like Belgium and the Netherlands had just completely evaporated them, basically. And what you're seeing is the material coming up and then spreading out in a mushroom cloud, like we see in nuclear explosions. So that dark material, the rocky, powdery material, is then spread outwards. And that clogs up the atmosphere, it clogs up the sky. It spreads across the whole of the Earth, and it blocks out the sunshine. The first thing that happens is that particles, dust particles, are red hot. They're ripped out of the ground, so they get very, very hot. The stuff that falls back to Earth is still really hot, and it sets fire to everything. So grass and trees, anything flammable will catch fire because of the heat from these objects falling back down. So you have fires everywhere. So if you weren't squashed and burnt by the object coming out of the sky, you could be set fire by all this other stuff. So all over the Earth, in a few days, you've got burning hot material, dust and ash falling out of the sky, setting fire to everything. So the Earth burns. This left-hand track is other burning type things. Okay? The air we breathe is nitrogen, mostly, 80% nitrogen, roughly. If you burn nitrogen, you make nitric acid. So as this object rips through the atmosphere, remember that image we saw of the meteorites, Challeybinks, where it burns through the sky? Imagine that kind of happening. It's basically producing nitric acid, which rains out of the sky. If it hits sulfur-rich rock, it produces sulfuric acid. So acid is a big problem. That acid goes up into the atmosphere, it rains back down, it changes the chemistry of the oceans. It acidifies them, okay? So it changes the chemistry. That dissolves sediments and things, it changes the chemistry of the rocks, and it releases carbon dioxide. And we know carbon dioxide is a global warming gas, so all of this side of things is creating global warming. So for the first few days, weeks, months, the Earth gets very, very hot. The sky is on fire, stuff is falling out of the sky and setting fire to the land. You can't breathe the air because it's now CO2. It's a really nasty place to be. After a few weeks or months, the red hot material in the sky cools down. It stays up there for decades probably, but it gets dark. And that black dust blocks out starlight, sunlight. So you can't see the stars, you can't see the moon, you can't see the sun. It's pitch black all day and all night. If it's pitch black, no sunshine, it gets cold. So after a period of warming, it now gets really, really cold. The temperature drops, we think, by at least 20 degrees Celsius. The average temperature in Scotland is, I don't know, probably 25 degrees all year round, roughly, someone told me. Tim was assuring me it was like 32 degrees last week. You know, it's going to be freezing all year round, literally, and below freezing in the winter. So the Earth gets very cold. We call it a snowball Earth. Gives you an idea of how cold it's going to be. But of course, if there's darkness and no sunshine, the plants die. No photosynthesis, so plant life begins to die. If the plants die, the plant eaters die. And then the meat eaters that eat the plant eaters, that eat the plants, they die. The whole food chain collapses. So you get global starvation. So the Earth is burning, it's melting, it's freezing, it's starving, and you've got things like tsunamis. If this thing hits the ocean, which most of the Earth's surface is, it generates huge waves. If it hits the land or even the seabed, it creates earthquakes, massive earthquakes, much bigger than anything we've ever experienced before. It could punch through the rocks and generate volcanoes. It could rip through to the liquid rock underneath. From young people's point of view, all their electronics are going to blow up. The whole internet goes down. No one has Facebook or Twitter or anything for forever, probably after. EMP, electromagnetic pulse. The Earth is a big magnet. These objects, even the comets, have a lot of metal in them. So if you move a magnet and a metallic object next to each other, through each other, if you like, around each other, you generate light, you generate radiation, electromagnetic radiation. And you generate microwaves, basically, with these kind of events. So if you want to find out what this is like, put somebody's iPod or whatever into a microwave and see what happens. Basically, you microwave the Earth. So the part of the Earth, as this thing rushes towards the Earth, in front of it is a blast of microwaves that takes out all the satellites, power stations, all sorts of things. So we lose communications. All that stuff goes down. And then all over the Earth, you've got these fires. So this is the kind of scenario for the end of the world. This is what happens. And this is what we think happened to the dinosaurs. The internet didn't go down for them because they probably didn't have it at the time. I know it's hard to believe an age without the internet, but apparently the dinosaurs didn't have the internet. And we found fossil evidence that it was clearly a meteorite. But literally, just to finish off, there is some real evidence. There is some, I'll just put you to the final evidence that we think. This is what the Earth looked like 65 million years ago, right? This is how we think it was. So the light blue bits are now land, but were ocean at the time. That little red square is a bit of a giveaway. That's where we think the crater is. It's in the Gulf of Mexico. I've drawn it onto Aberdeen roughly to show you how big the crater is. Right? Give you a sense of the scale of this thing. So it's in the Yucatan Peninsula, so the nice holiday bit that everyone goes to. Half on the land, half in the sea. And at the centre of the crater, roughly, is a town called Chicxulub, which kind of spookily translates the tail of the devil. So it's got kind of a slightly spooky, mystical name. But we think this is the crater that killed the dinosaurs, but you can't see it anymore. You can only see kind of the very outline, a very faint outline of it. So NASA maps a few years ago revealed that there's a little dip in the land. So on the outside of this dotted line, the ground is about a foot higher than it is on the inside. There's a little trough, about a foot deep, that marks off the edge of the crater. And around the edge of that crater are these things called cenotes. These are holes, sinkholes. Better image. This is a map showing you the light blue dots are where the sinkholes, the cenotes, are. And the Aztecs and the Incas and the ancient civilization thought these were entryways to hell, to the underworld. So again, it's slightly spooky. But you can see a beautiful semicircle outlining the edge of the crater where the rock is all smashed up and collapses. And on the right-hand side, again, maybe evidence that the object came in from the top left to the bottom right and caused all the damage in that direction. So we have some nice evidence. But the real data came from geologists, from the oil companies looking for oil in the Gulf of Mexico. And they found in gravity data, for example, this sort of strange circular feature. You can see the coastline in white. It's about 180 to 200 kilometers across. It's huge. So like I said, 20 times the diameter. That implies an object 9 to 10 kilometers across, 5-6 miles across. So we know impacts are a natural thing, right? That's what made the solar system, what made the moon. It's a natural process. We see lots of evidence for big impacts all over the solar system. We can find craters, big craters, of about the same age as those mass extinctions, apart from that really big one, the Great Dine, which we now think we have found some craters for, but the evidence is still a bit weak. You can choose your method of death, right? There are lots of ways you could be killed by these things, and all of these would happen over decades, maybe hundreds of years. The Earth would suffer. So you can see they have a massive effect on life on Earth. There's nothing we can do about it. You can watch Deep Impact and Armageddon. You can watch Bruce Willis blowing up a meteorite and an asteroid and say that isn't real, sadly. But in the future, you could say people might look at the economic opportunities of mining asteroids, either for their mineral potential, gold, silver, platinum, that kind of stuff, but also using them as kind of little spacecraft. We can grab onto one when it's close to the Earth, build a little colony on it, and then ride it out into the outer solar system. It's a kind of a cheap way of getting out to the outer solar system without having to build rockets to do it for you. So, I will finish there. Apologies for rattling on a little bit, but I hope you've learned something about how the world has ended in the past for other species and how it might end for us in the future. But at least we'll see it coming. If that's encouraging, I don't know. Thanks very much.